All right, so what we're going to do today is we're going to finish up chapter 5. We're going to talk about the Poisson distribution, and we're going to begin chapter 6. And in chapter 6, we'll discuss the uniform distribution, and we'll also discuss the normal and standard distributions. Okay, first today we're going to take a look at a Poisson distribution. And for whatever reason, my computer is moving really slow. Okay, we're going to talk about the Poisson probability distribution. And in a Poisson probability distribution, we talked about random variables in the last class. We talked about the two types of random variables. There are discrete random variables, and again, discrete means there's a countable set. And we also talked about continuous random variables. And for continuous random variables, they kind of deal with in-between sort of things on infinite scales. Discrete probability distribution, an example of that would be the Poisson probability distribution. And it's the distribution that applies to occurrences over some time interval. Okay, so all of the distributions we talked about so far, the binomial distribution, there were certain characteristics of a binomial distribution. For a Poisson distribution, it's the occurrences over some interval time. And the random variable is actually the number of occurrences in the interval. Okay, just like just like in the binomial probability distribution, there was a formula. There's also a formula for the Poisson probability distribution. And here it is. It's given as P of x is equal to mu raised to the power of x. So again, mu is the mean, times e, and this e is exponential e, and it's actually a constant that has a value 2.718. It's e to the negative mu divided by x factorial. All right, where mu is the mean. We're going to talk about the mean in a second. And this exponential e, if you take in college algebra, you kind of dealt with this exponential e, but if not, just notice that e, sort of like pi, is a constant number. Okay, that's not a variable. It actually is assigned a value. Now, while we're talking about the Poisson distribution, and we talked about in the previous slide, it was a number of occurrences. Here's some examples of Poisson distributions. A Poisson distribution could be the number of, let's say, internet users in one day. So notice we have the occurrence, which would be an internet user. We have a time interval, which is 1 day. Another example could be, let's say, the number of patients arriving at an emergency room in 1 hour. So notice we have that time interval, which is 1 hour. And also something like the number of hurricanes. Okay, since we're in hurricane season, all right, we can look at that as a Poisson distribution. Okay, and here's the formula that drives those distributions. All right, now we'll take a look at, well, here are the requirements for Poisson distribution. The random variable has to be the number of occurrences of the event in some time interval. The occurrences must be random. The occurrences must be independent. And they also must be uniformly distributed over the interval being used. Now, this uniformly distributed, what that actually means is that the likelihood of, let's say, the likelihood of success, or whatever your occurrence is, would be the same over for every instance. For example, a deck of cards is uniformly distributed because you have an equal chance of drawing a spade, a heart, so on and so forth. A coin toss is also uniformly distributed. Okay, it's uniformly distributed because there's an equal likely chance of a head or a tail. Okay, so for the Poisson distribution, notice that the occurrences are uniformly distributed. Okay, which means that they all have an equal chance of probability. All right, so here is the mean, the formulas for the mean and the standard deviation. The mean is known as mu, and we'll see that there's not an actual formula that says this equal to something. We'll see how the mean of a Poisson distribution is calculated in our example. The standard deviation, okay, and this funny looking symbol, that's a Greek alphabet, sigma. Sigma is equal to square root of mu. Right, so the mean is mu, and the standard deviation is the square root of mu. All right, so let's take a look at an example. Okay. So it says for the 55-year period, since 1960, there were 336 Atlantic hurricanes. And we're to assume that this is a Poisson distribution, okay, which means that this meets all the 4 requirements previous. Okay, there is some time interval, and it's important to note the time interval because the number of occurrences divided by the time interval will give you the mean. We're asked to find the mean, and then we're asked to find the probability that exactly 8 hurricanes in 1 year. All right, so I'm going to go back to our document camera. Okay, and from our example, it says for a 55-year period, and as far as determining which distribution we're working with, in the problems, you'll be given the distribution. Okay, so there's no need to trouble on which, distribution. Is it binomial? Is it Poisson? Is it uniform? Is it normal? Those things will be given to you in the problem. It says for the 55-year period, since 1960, there were 336 hurricanes. Right. So this is a Poisson distribution, and we're going to find the mean, which is mu. So now, even though there wasn't a formula per se on the other slide, here's a rough formula for the mean of a Poisson distribution. The mean of the Poisson distribution can be the number of occurrences divided by the time interval. Okay. Now, sometimes your time interval may be given in days. Sometimes the time interval may be given in years. Okay, so the time interval depends on the problem. All right, so we compare that with the information we're given. It says for the 55-year period since 1960, there were 336 hurricanes. So the number of occurrences, or the number of hurricanes, is 336. And the time interval, which is in years, is 55. So we can calculate our mean by dividing 336 by 55. And if I pull out my calculator, I would get, or we would get 6.109. I'm just kind of rounding to the thousandth place. It'll tell you in the directions on the place value. So this would be the mean. And next we're asked to find the probability of 8 hurricanes. Of exactly 8 hurricanes. Now we're actually going to look at this two ways. We're going to look at this by using the formula, and then we're going to look at this by using the calculator. Now I don't expect you to use the formula that I'm going to use for every problem. Okay, but I just want to show the similarities on that formula, because there is an actual formula driving the probability. Show the relationship between the formula and the calculated results. All right, so there was a formula, and here's the formula. It was P of X is equal to mu raised to the power of X, or mu raised to X, times e to the negative mu over x factorial. All right, so the only two values we need in order to calculate this distribution, we would need x and we would need mu. All right, so we'll take the Poisson probability distribution formula, and we're going to substitute x for 8, right, because we're finding the probability of exactly 8 hurricanes, and we're going to substitute mu for 6.109. All right, so I'm going to write this out as P of 8 is equal to mu, which is 6.109 raised to the 8th power times e, so remember e is at 2.718 number, raised to the negative mu, so that's negative 6.109, and we're going to divide that by 8 factorial. All right, so when I calculate that on my calculator, I believe you should get 0.106. All right, so I'm actually going to go back to the document camera screen, and I'm going to calculate it on the calculator. All right, just so you can see how that's done. All right, so I'm going to put in our numerator, which was, and I'll put this in a set of parentheses just to be mathematically correct on this. We'll take the numerator, put that in a set of parentheses. So this is 6.109 raised to the 8th power times, and this exponential e, if you're not used to working with that, it's above this ln or natural log key, and it's yellow, so I'm going to hit second and ln, which is e. Notice it gives me a begin parenthesis. I'm going to put in negative 6.109. I'm going to close off my exponential e function. I'm going to close off my numerator. We're going to divide by 8. And here again, I'll put the denominator in a set of parentheses. I'm going to divide by 8 factorial. So again, for factorial, you have to go in math to probability. And you get 1.693. Okay. So I'm actually write that out as 1.069. So now, how do you use the calculator? Right. I guess before I ask that, any questions on how we actually calculated this? All right, so in order to use a calculator, and I'm going to go back to the document camera for just 1 second. All right, so this was our rough calculation for the probability of 8 hurricanes. All right, in the calculator, we're going to use the Poisson Pdf. Okay. So remember now, we have the PDFs and the CDFs. The PDF will give you exactly 1, exactly 2, exactly 3, so on and so forth. And then we had the Poisson CDF, and in the Poisson CDF, the CDF will give you the cumulative distribution. So like if you were finding a CDF of 8, the difference between the PDF of 8 is that the PDF of 8 will give you exactly 8, which is what we're calculating. The CDF of 8 would give you the probability of 1 plus the probability of 2 plus the probability of 3, so on and so forth. And it will also give you the probability of 8, and it would add all of those probabilities together. In the last class, we saw an example of that using the binomial distribution. So that cumulative concept is the same for all of the CDFs. So the Poisson Pdf is used to calculate the exact value. Okay. So since we're finding exactly 8, we're going to use the PDF. Now, similar to the binomial PDF, you had some parameters. I believe you had to put in n, which was the number of trials. You had to put in P, which is the probability of success, and you also had to put in an X value. The Poisson Pdf also has parameters. It only has two parameters, which are mu and X. So using the calculator, if we wanted to calculate this P of 8, you know, which was this 0.1069 value, if we wanted to calculate that using the calculator, we would use the Poisson Pdf. All right. So for the Poisson Pdf, we would put in, so P of 8, and you really can't see that. All right, P of 8 is equal to the Poisson Pdf. That's PDF. We would have to put in mu. So from our previous calculation, mu was 6.19, comma X, which is 8. Right, so this is what I'm going to put in my calculator. So I'm going to go into distribution. So it's second and variables. I'm going to scroll down until I get Poisson Pdf. Right, so we're calculating the exact value, so we're using the PDF. I'm going to put in mu, which is 6.109. I'm going to put in comma. I'm going to put in 8. And notice we get the probability 0.1069. Okay, we get exactly the same probability as the formula. So that's equal to 0.1069. All right, so any questions on the Poisson distribution? All right, so now we're going to move on and we're going to talk about the normal distribution and the standard normal distribution. Okay, so this is all titled as normal probability distributions. All right, so the first type of distribution is a uniform distribution, and the uniform distribution is not actually a normal distribution. So give me 1 second. Sorry, let me just change this. Okay. So we're going to talk about the uniform distribution, and we're also going to talk about, okay, I'll kind of fix this later, and normal probability distribution. All right, so first we're going to talk about the uniform distribution. All right, so I believe this will make the third distribution we talked about. We talked about binomial, Poisson, and now we're talking about a uniform distribution. And for the uniform distribution, it says the area under the graph of a continuous probability distribution is equal to 1. All right, so the uniform distribution and the normal and standard normal distributions, they deal with continuous random variables. The uniform distribution deals with the area of a continuous probability distribution, and that has to equal 1. Okay. From this point going forward, I want you to know that area and probability are one and the same. So if we're looking at probability distributions and we're asked to find the area, we're also asked to find probability. If you're looking at a probability distribution and you're asked to find the probability, that's also the same thing as the area. The uniform distribution deals with rectangles, so to speak. We're going to see how that works. So we're going to kind of review a basic on how to find the area of a rectangle. Okay, and you'll see how that comes into play as far as the uniform distribution is concerned. But just be mindful that the area for the uniform distribution has to equal 1. Right. So here again for number 2, sort of going back to the rectangle and the area for a rectangle. So let's review this. All right, so if we have a rectangle, and you'll see how this all plays a part in just a second. In a rectangle, we have a quadrilateral four-sided figure with the opposite sides being parallel and congruent. Congruent means they're the same size. So these two sides would have the exact same measure, and these two sides would have the exact same measure. We're going to call this the width. This side is the width, and this is our height. And simply to find the area, and again, the area and probability are exactly the same. The area is the amount of surface a figure would have. All right, because then you're going to see some shaded figures. So the shading or the area, all of that's probability. All right, so the area is the amount of surface something has. And the area for a rectangle is simply the width times the height. All right. All right, so remember that the area is the width times the height, and for our uniform distribution, the area has to equal 1. All right, so let's take a look at the example. It reads, during certain time periods at JFK Airport in New York City, passengers arriving at the security checkpoint have waiting times that are uniformly distributed right? So even though you kind of see the time interval thing going on, wait times, it tells us that it's uniformly distributed, okay? So that would supersede any notions that this is a Poisson, okay? And it doesn't fit all of the properties to model it by Poisson, okay? But it tells us that it's uniformly distributed between 0 and 5 minutes, and we're actually find a probability that a randomly selected passenger has a waiting time of at least 2 minutes. All right, so I'm going to switch back to the document camera. Right, and this is a uniform distribution. So I'm going to abbreviate the problem. So we have passengers arriving at JFK Airport have waiting times that are uniformly distributed between 0 and 5 minutes. Right. Find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. Okay. So this at least 2 minutes means that the person could have a waiting time of 2 minutes, 3 minutes, 4 minutes, or 5 minutes. All right, because at least 2 means 2 or greater. All right, so let's kind of sketch something like this out in a rectangle form. All right, so here's what I mean by rectangle form. First off, I am dealing with some type of rectangle. On my vertical axis, or x-axis, if you want to think of this thing on an x and y axis, I'm going to have the waiting time between 0 and 5 minutes. So this is waiting times. So this would be 0, 1, 2, 3, 4, and 5. All right. And for my vertical or my y, I would have the probability P of x. Now keep in mind what's special about this uniform distribution, that it must have an area of 1. All right. All right, so how can I find the height? Well, we have the fact that the area is equal to 1. Right, so over here, I'm going to kind of do some scratch work. So the area is equal to the width times the height. For a uniform distribution, the area had to equal 1. So I'm going to substitute the area with 1. And if I look back at my rectangle, this is my width. And this is my height. Right. So now what is my width? Well, my width is going to be 5, right? 5 minus 0 is 5, and I have 5 spaces. 1, 2, 3, 4, 5. So my width is 5. So right here I'm going to put width is equal to 5. And what's my height? Well, I don't actually know my height. So I'm going to just write height. I'm going to put that in the set of parentheses. So I have 1 is equal to 5 times the height. Now I need to solve for the height. All right, so I'm going to divide both sides by 5. So 1/5 is equal the height. So my height is equal to 1/5. Well, I'll write it here. The height is equal to 1/5. All right, so my height is equal to 1/5. So this is how I calculated that height. Right, I used the formula that area is equal to the width times the height. For a uniform distribution, the area has to equal 1. I can always pull out my width, right? So my width is 5, and I don't know the height, right? So I just left that as height. In order to solve for height, I divided both sides by 5, so 1/5 is the height. Now, I believe on some of these problems, they may not write it as 1/5, they may write it out as a decimal, 0.2 or something like that. Okay, but this is how you determine the height. But now, how does that help us answer the question? We want to find a probability that that a randomly selected person has a waiting time of at least 2 minutes. All right, so if I go back to my diagram, right, and if that person has a waiting time of at least 2 minutes, that means that that person can have a waiting time of 2 minutes, 3 minutes, 4 minutes, or 5 minutes. So I want to take that interval 2 to 5 and I want to find the area. All right, so I'm going to find this area or find the probability, because remember that area is probability for this figure, this rectangle. So the probability of at least 2, all right, I'm simply going to find the area. I'm going to take the width. So the width here is 1, 2, 3 times height, and the height is 1/5. I'm going to multiply those two together to find the area, which is the probability. So the probability of at least 2 people is the area. So I'm going to take the width, which is 3, right? 1, 2, 3 times the height, which is 1/5. And 3 times 1/5 is 3/5. And if we convert 3/5 to a decimal, because normally these probabilities are going to be given to you in a decimal form. We get 0.6. All right, so anytime you're dealing with a uniform distribution, keep in mind that it must have an area of 1. Based on the fact that you're given the area, you always have to find the height. Right, so you can lay it out in the form of a rectangle. If you're at whatever you're asked to find, okay, here I was asked to find a probability of at least 2, right, 2 or more. So I sketched that out as a rectangle, found the area. All right, any questions about the uniform distribution? All right, I'm going to switch back to the application screen. And we're going to talk about the normal distribution. Okay, so here's the normal distribution. Now, the normal distribution is also called the bell curve or the bell-shaped curve. Okay, I don't know if you may have heard that before. So notice that uniform distribution took on the shape of a rectangle. This is sort of taking on a Taco Bell, a bell sort of shape, and this is the normal distribution. Now, in the uniform distribution, keep in mind that everything had an equal chance of being selected, right? For this normal distribution, it's a little bit different. For the normal distribution, if we take a look at the mean, most of the values are near the mean. All right, so there's not like an equally likely chance. Okay, an equal likely chance would, everything would have the same probability, right? And from the passenger problem, everyone had the probability of 1/5, right, throughout those 5 minutes. So that gave us a rectangle shape. Here, notice we have a bell shape, and the mean, or the majority of the values, will lie at the mean. And here's the formula for a normal distribution. Right? It's a continuous random variable, and its graph has what's called a bell shape, and it's symmetric about the mean. And this is the form. It's quite complicated. Y is equal to, here again, there's that exponential e raised to the -1/2 times the quantity x minus mu sigma squared divided by sigma times the square root of 2 pi. All right, so this formula contains both e and pi. Keep in mind which are constant numbers. Now, when we calculate things using a normal distribution, such as the other distributions, I'm going to take my calculator, I'm going to go into distribution, and notice I have the normal PDF and the normal CDF. Here again, the PDFs, they calculate the exact value. The CDFs are a cumulative probability calculation. All right, so that PDF, CDF concept is in all of our distributions. Here is what's called a standard normal distribution. And here again, a standard normal distribution, it takes the bell shape. The area is equal to 1. So here again, area is probability. In this standard normal curve, So in the calculator, when we're given the fact that we're dealing with a standard normal distribution, notice I don't see standard normal, I just see normal. The standard normal distribution is a special kind of normal distribution where the mean is 0 and the standard deviation is equal to 1. Now in a second, we're going to see how we actually can convert from the normal distribution to the standard distribution. That's by using something called a z-score. Okay. So let's kind of further examine the standard normal curve. So just notice that it's centered, so to speak, at 0. And I have 1, 2, 3, and again, these are standard deviations. This is 1 standard deviation to the right, 2 standard deviations to the right, and 3. One thing about standard normal distribution is that this thing keeps on going forever and ever in both directions. All right, so when we calculate things in our calculator, we're not going to use exactly the range from 3 to -3. We're going to use ranges that are slightly smaller or bigger. All right. So to actually look at some problems, I'm going to pull up some homework problems to actually explain these. Okay, give me 1 second. I think okay, I'm back on track. I'm going to go into my math lab. And from this point, we're just going to take a look at some problems and we're going to use a calculator. All right, so we won't be actually dealing with showing the calculation on that formula. All right, the normal distribution formula. Okay, chapter 6. All right, this is taking my computer a while to bring up these documents. Okay, give me 1 second. All right, so I'm gonna just fast forward a little bit. Okay, problem number 2. Okay, that was a uniform distribution. So basically similar to the problem that we did in class, I kind of laid it out from 0 to 5 minutes. And we were looking for passengers with a waiting time of 4.25 or greater. Right. So I kind of just mapped that out as a rectangle from 4.25 to 5, right, which would be 0.75. And I multiplied that 0.75 by 1/5, right, to get this 0.15. Problem number 3 is the same way, okay, a uniform distribution. So I mapped that out between 49 and 54 minutes, right, using a rectangle. I found the probability, right, and then I sort of found this area or this rectangle. All right, then we get into these sort of problems, right? So keep in mind it says find the area. Area is probability. All right. So now keep in mind we're finding the area of a shaded figure. In order to answer this problem, it says find the area of the shaded region. The graph depicts a standard normal distribution with a mean of 0 and a standard deviation of 1, and we're asked to find the area. So let's see if I can pull up the windows sort of side by side. All right, so just notice from our standard normal curve, this thing runs from like -3 to +3. So what I want to do is I want to calculate the area from -3 to 0.74. Okay. But notice now, this thing, even though this goes, it appears that it stops at -3. This thing actually keeps on getting smaller and smaller and smaller. All right, so this is what I'm going to do to account for that. I'm going to pull up my calculator. And since we're calculating the probability of not exactly one value, we're calculating the probability of a shaded area, I'm going to use the CDF. So I'm going to go in the second distribution, and I want to use the normal CDF. And I'm basically going to put in an interval. I'm not going to put in -3 to 0.74. I'm actually going to use -10. And the reason that I'm using -10 is because I want to cover all of this area to the left. Right, so never use -3. I always use -10 and +10. All right, since I'm finding the area to the left, I'm using -10. I'm going to put in a comma. I'm going to put in 0.74. I'm going to close that off, and I'm going to hit enter. All right, so that gives us the area or the probability from -10 to 7.4, which is all of this shaded area. All right, we're actually around 4 decimal places, so I get 0.7704. Right, so any questions about this problem? So since I'm finding the area, all right, of a shaded region, I'm using the CDF. Okay, let's take a look at some further examples. Let's take a look at this one. I'm going to blow this up slightly. All right, so here again, we're asked to find the area of a shaded region. I'm asked to find the area from negative 0.95, all right, to like positive 3. Right, if I go back to our standard normal, right? But here again, I'm not actually going to use 3. I'm going to use positive 10. Okay, so notice I'm using negative 10 to the far left and positive 10 to the far right. But you want to make sure you put it in interval form. Right, so I'm going to recall the normal CDF function. So that's second in vars, which is distribution. Oops. I want normal CDF. I'm going to put in negative 0.95, comma 10. And that gives me the area of the shaded region, 0.8289. All right, so any questions about the first couple of problems? All right, so notice that they tell us that they're normally distributed and it follows a standard normal distribution. Okay, and then we run into a problem such as this. So what I want you to notice about the two previous problems to this problem is notice that here I'm given a z value on my horizontal axis. Right? And before, I'm going to go back. Right, I was actually given the area. I was actually given the z-score. All right, if I go back another problem, here again, I'm actually given the z-score. If I go back to problem number 6, here I have to find the z-score. All right, so how do I do a problem like this? All right, before we do this problem, let's actually talk about what z-scores are. All right, so when we convert from a non-standard normal distribution, so what that means is in a non-standard normal distribution, our mean can be anything. Like if we're dealing with scores, the mean score could be an 80, not necessarily a 0. Okay, we standardize everything at 0. So non-standard normal distribution, your mean can be, let's say, 80. Your standard deviation can be like 15. We standardize those things in the standard normal deviation by forcing the mean to be 0, and we force the standard deviation to be 1. And we use this formula. The z-score, or z, is equal to x minus mu divided by the standard deviation. Okay. So if you know the mean of your standard deviation, if you know the mean of your distribution, if you know the standard deviation of your distribution, you can convert that non-standard distribution to a standard distribution by using this formula. Okay, so that z is actually called a z-score. Okay, so how do we find z-scores in the calculator? Oops. Give me 1 second. I think I have closed the application screen. All right, so how do we find z-scores? Well, I'm going to go back into distribution, which is second inverse distribution, and there's something called inverse normal, INVNORM. For the inverse normal, it only has the parameter of one value. Okay, you only put one thing into the inverse normal, right? And it'll give you the z-score. What you actually put in is the area. Now, unlike the normal PDF, you could insert two values, right? You could put in your interval, right? When we use the CDF to calculate our areas. However, the inverse normal requires only one parameter. It sort of has the CDF function where it calculates all of the area to the left. Okay. So for example, in this problem, I want to convert this area to a z-score, so I'm simply going to go in the inverse normal. I'm going to put in 0.8531. And if I were to round that to 2 decimal places, that gives me my 1.05 once I round. All right, so just notice how this figure looks. Right, I'm not giving a shaded value to the left. I'm not giving a shaded value to the right. I'm actually giving the area at this particular z-score. I'm going to move to number 7. And I don't want to generate any other examples because I don't know if this thing is going to change or not as far as flipping my area. All right, so here again, we're asked to find a z-score. So they give us an area. So this is what I really want you to keep in mind. The inverse normal, as well as all of the other CDFs, they calculate the area from left to right. So notice the shaded area in this figure is to the left. So in order to figure out what z-score has an area or probability of 0.2236, I'm simply going to go into inverse normal. And since this area is to the left, I'm going to put in 0.2236. And I get negative 0.76 as a z-score. All right, so far so good with inverse normal. If I'm not giving any shade at all, I simply put in the value. If I'm given the area and it's shaded to the left, because remember this inverse normal as well as the CDFs, they calculate area to the left. I also put in that area, 0.2236. This is where you're going to start to run into a problem for these type problems. And the reason why we're running into a problem, because here again, we're given the area and we're asked to find the z-score. When I use the inverse normal, it gives me the area only to the left. All right. So how would I find the area to the right? Well, keep in mind that the total area under the curve is equal to 1. Right? Just as a fact on dealing with the normal or dealing with the standard normal. So if I wanted to find, let's say, this area to the left, I would have to subtract from 1. So in my calculator, I want to put in inverse normal. But this time, I'm not actually going to put in the 0.7939. I'm going to put in 1 minus 0.7939. Right? So what this actually gives me is it gives me the area to the left, and it's giving me the z-score for the area to the left, not for the area to the right. So this is where you have to be careful when you're calculating the z-score given an area. If that area is to the right, then when you're using your inverse normal function, you must subtract from 1. I believe the rest of the problems, they sort of deal with that same concept here. You're asked to find the probability that a given score is less than negative 1.36. So here again, I had to find the area shaded to the left of negative 1.36. And to find the probability, remember I'm finding the area. So I used the normal CDF from negative 10 to negative 1.36. Okay, for the last problem, I believe we'll take a look at a problem on how we actually calculate a z-score from a non-standard normal. Okay, so all of these problems I'm kind of thumbing through, they're similar to either finding the area using that normal CDF or finding the z-score using that inverse normal. Okay, I see that we're running out of time. I don't know if you may or may not have another class. We will pick this up again next Wednesday. Okay, we'll kind of pick it up from here. We'll finish the chapter, and then our test would be that following Monday. The chapter 5 test, okay, the uniform stuff test, the uniform distribution and the normal and state normal distributions won't be on the chapter 5 test. However, you will see some problems dealing with that Poisson distribution we talked about. And I have that test set for Friday. If you need more time, normally the tests are on Monday. I believe I'll just go in and set that for Monday just so all of the tests kind of fall on a Monday. I think I have it set for Friday now. I'll go back in and I will set that for Monday. All right, I'm going to go back to the document camera and I'm going to ask, are there any questions about anything up to this point? Okay, there's some comments in the chat. Let me see if I can pull those up. It says, how do you calculate the normal distribution on the TI-84? Okay, give me 1 second. I'm going to get my handheld 84 because that is right. The keystrokes are a little bit different. Give me 1 second. I'm going to get my handheld. Okay, sorry about that. For whatever reason, I got cut off. Okay, sorry about that. For whatever reason, I just got cut off. But I have my TI-84, the handheld. So if you were to calculate, let's say area using the TI-84, I'm going to go on the distribution. Right, you'll find distribution. You're going to find normal CDF, and the problems that we were putting in, like 10 and let me see if I can bring those up again. All right, if you're dealing with a standard normal, notice that it already has the mean as 0 and the standard deviation is 1. Whenever it says standard normal, all right, those are your settings, 0 and 1. And you're simply putting in your lower limit. So let's say I put in -10. You'll put in your upper limit. I believe the first one we did was 0.74. Right, you would leave your mean as 0. You would leave your standard deviation as 1. I hit enter, so it put it on my home screen. And once you hit enter again, right, it would give you your 0.77, whatever your area or your probability is. For the inverse normal problems, I'm going to go to second, distribution, inverse normal. So here again, you have the same thing. For the problems all of the problems we did today, the mean is 0, standard deviation is 1, and this thing will still calculate the area from the left. Right? So if we were to put in a value like 0.8667, you would get a z-score of 1.11. So the only difference is, I believe, on the 83 that I was actually using in the lecture notes and on the screen, the 0 for the mean and the 1 for the standard deviation are automatically set into that function. Okay. And on the 84, the functionality is set up a little bit different. All right, any other questions? Well, first of all, I guess, does that clear that up for you? Okay. All right, any other questions about anything up to this point? Okay, there's something in the chat. Okay, thank you. All right, Jillian, no problem. All right, well, I guess if there's no other questions, I'll see everyone on next week.